So today I wanted to go over a pretty nice calculus technique, an integration technique in specific, that we can use to evaluate some integrals that might otherwise seem untouchable by direct methods such as by parts or partial fractions or what have you. So generally this is referred to as Feynman's technique or the Leibniz rule, or you may even hear it as differentiating under the integral sign. And what we're trying to do here is parameterize an integral as some function with some specific variable, and then use that parameterization to manipulate the expression on the inside and simplify it to an expression that's more directly solvable. So what I have listed here is the Leibniz rule, which tells us that for two constant functions a and b, that we can express the derivative of the definite integral of those bounds of some function of x and t with respect to t as that definite integral of the partial derivative with respect to x of that function of x and t with respect to t. And this is going to be the driving force behind the Feynman technique, as we'll see. So I think the next thing to do is just go straight into the example. So let's consider the improper integral from 0 to infinity of e to the minus x squared cosine of 5x. And this integral might already seem pretty scary because we have the Gaussian inside of our integral, the e to the minus x squared, which we know is defined by the error function, or more specifically, we can find a closed solution that is famously the square root of pi, but we know that it's not that easy to solve with direct methods. Either we have to utilize multivariable calculus or some tricky manipulation using single variable calculus. But in our case, we want to solve this integral using Feynman's technique. And so the first thing we need to do is parameterize our integral. So I want to define a function f of beta, and I want this function to just be the integral itself. But I specifically need to parameterize it, so I want to replace this constant term 5 with beta. So we have beta x, and we're still integrating with respect to x. So the next thing we need to do is differentiate this. So I want the derivative of f of beta, which I'm just going to express as f prime of beta, just as shorthand notation. And then I want the derivative with respect to beta of the integral. So the only issue we have here is that we're trying to differentiate this integral with respect to beta, but our integral is dependent on x, but then we also have beta. So what do? Well, we use a partial derivative from multivariable calculus. And so if we remember what the partial derivative is, it means that anything that's not the dependent variable, which in our case is going to be beta, we are going to treat as a constant. So the next thing I want to do is evaluate the partial derivative of this inside function so that we can rewrite our integral, because we can't leave it like this. So the partial with respect to beta is going to be very nice because we can just take out this e to the minus x squared as a constant because there's no beta term in it. And then cosine beta x. This is just going to be a very simple chain rule. So we're going to have e to the minus x squared. So we want the derivative of the outside times the derivative of the inside. So the derivative of cosine is negative sine. We still leave the inside the same, so beta x times the derivative of the inside, which in this case is just going to become x, because we're differentiating with respect to beta. So now I have f prime of beta is equal to our integral, and this integral can now be expressed as negative x e to the minus x squared sine of beta x. So now this integral is doable. We can use integration by parts to solve it, And that's all because of this minus x term in the front. And now it's no longer a pure Gaussian integral. And to do integration by parts, we can just use the uv minus integral of v to u, or in this case I'm going to use tabular integration just because we know that this is going to have oscillatory behavior because we're dealing with e to the minus x squared and sine of x, which are just going to go back and forth between sine and cosine and e to the x itself. So how do we set up our tabular integration? Well, we want one column to be differentiation and one column to be integration, and then we have our signs here. So I want my differentiation of sine of beta x, my integration of minus x e to the minus x squared. So this is just going to be minus beta cosine beta x, and then 1/2 e to the minus x squared. And we are just, this is with respect to x, as you can probably tell. So now the last step is we know it's going to oscillate, so we're just going to go back to the same expression we had originally. So we are going to take this beta x and replace it. So we ended with what, sine of beta x over 2e. This negatives are going to cancel out, so positive x squared. And this is evaluated from 0 to infinity. And then minus, the only term that would come out is this, times the integral of e to the minus x squared cosine beta x dx. And this is what I mean by oscillatory behavior, is we're going to end up with the original expression because it's going to oscillate between sine and cosine when we take the derivatives or antiderivatives. So this expression on the left side is our antiderivative. So we can just straight up plug in our points and solve it. Or in this case, we can plug in 0 and then evaluate the behavior at infinity. Using a limit, I'm not going to specifically specify the limit notation, but you can get the idea. So I know that e to the x squared is going to grow and grow and grow, but I know because that denominator is going to get really large, it's going to tend to 0. So this is just going to be equal to 0. And then we have minus beta over 2. But if you couldn't tell, this expression here is just our function f of beta that we defined earlier as the integral of v to the minus x squared cosine of beta x. So I'm just going to replace this full integral with f of beta because they're equivalent. So now we have still that we're solving for f prime of beta. So we have that f prime of beta is equal to 0, which just goes away, and then we have minus beta over 2 f of beta. And while we want to solve for f, but now we're in a different predicament. We have, all we ended up with is that the derivative is equal to this expression that depends on the function f. So, well, how do we solve this? Well, this is a differential equation. Specifically, it's a separable differential equation, a separable first-order differential equation, which is very nice for us because it's the most basic form of a differential equation that we can solve. And so to make this more clear, I'll rewrite it as df d beta equals minus beta over 2 times our function f. So now we have this differential equation. So if we want to find f, let's just solve the differential equation. And because this is separable, we can simply divide by f. So we'd get 1 over f df. And then we can multiply by the reciprocal of 1 over d beta, which will cancel out that beta on the left side and give us d beta over here. And so now all we have to do is just integrate. This is how we solve a separable differential equation. So I know that the integral of 1 over f is just going to be the natural log times the absolute value of f. That's just a very famous integral that everyone should know. We don't need to do any work to show that. And now the integral of minus beta over 2 d beta, well, let's just take out minus 1/2 as a constant. And so now we're just looking at the integral of beta with respect to beta. So that's just going to give us beta squared over 4. Or sorry, over 2. That's just the reverse power rule for integration. So now we have the ln, absolute value of f, is equal to, and I'll just multiply this 1/2 in, minus beta squared over 4. So the only complication we have now is that we want f, but it's encapsulated by this natural logarithm. So to do that, or to fix this, let's just use some algebra, specifically use e and the property of the natural logarithm, which is in base e, to cancel this out, and just end up with f, and then e to the minus beta squared over 4, and because we integrated, we want some constant. So generally, though, we express these solutions of differential equations as our constant in the front, which we generally call a, e to the minus beta squared over 4. So now we've found f of beta. This is f of beta. I just wasn't being explicit. So then in your head you're saying, well, that's the solution to the differential equation, or to the integral, because we were trying to find f of beta, and we solved this integral and found what f of beta is. So now it's just a e to the minus b squared over 4. But we have to remember that we are dealing with a definite integral. We were given bounds, which is this case from 0 to infinity. So we need to find out what our constant a is in order to find the full solution. So let's rewrite this as, or let's rewrite f of beta as our actual integral. So 0 to infinity, e to the minus x squared, cosine of beta x dx is equal to a e to the minus beta squared over 4. And to try to find what a is, let's just let beta equal 0 and see what happens. Well, this would just turn into the integral e to the minus x squared, and then if beta were 0, we just get cosine of 0, which is 1. So we just end up with the integral of e to the minus x squared dx. And that would be equal to a, and then again we'd get e to the negative, or just to 0, so e to the 0, which is 1. So then we just get the integral from 0 to infinity of e to the minus x squared dx is equal to a. So now we have an expression for a. We know that a is equal to this integral. Well, okay, great. Now we have to solve another integral just to find this constant. Well, as I mentioned earlier, this is the Gaussian integral. This specifically is the Gaussian integral, just e to the minus x squared. And this very famously has the solution of the square root of pi over 2. So a is square root of pi over 2. So this worked out very nice for us, this Gaussian, because we were able to find our constant very simply. So now let's go back. Now we can say that our definite integral from 0 to infinity of e to the minus x squared cosine beta x dx is equal to square root of pi over 2 e to the minus beta squared over 4. Okay, we don't need plus c, we're solving a definite. So are we done here? Well, not entirely. This was not our original integral, if you remember. Sorry, we started with cosine of 5x, and we parameterized it as beta. So all we have to do then to find this is replace our beta with our original value for beta, which was 5. So we'd get square root of pi over 2 e to the negative 25, negative 5 squared over 4. And this is the solution to our integral. So what did we see here through this method? Well, we actually saw quite a few calculus techniques. We saw parameterization, which we use all the times for similar things. We saw integration by parts. We saw an ordinary differential equation. And we saw the Gaussian integral. So we saw 4 different things from calculus, really. Oh, and I guess technically we saw partial derivatives. That's from multivariable calculus. So this one integral, using this technique, utilized around 5 areas of calculus if we were to treat them independent of each other. So that's really all I wanted to go over was this method. I thought it was very cool, and I thought the solution to this integral was cool, and I thought it'd be fun to go over. I'm not really sure how helpful this will be to anybody, honestly. I think it might be helpful in physics, but I'm not sure. But if anything, it's at least a trivial method to solve some more complicated integrals. So maybe if you end up having a crazy integral like this, you might be able to use this method to solve it. So that's all I have.